Hi there. So as you can see on the board itself, Riemann integral from real analysis. This chapter is a well-known chapter and is studied by all students during graduation. And also Riemann was a great German mathematician. We're not going to go into his history. It was back in the 1850, and so he came up with the idea of finding the areas of functions under curves. And today, we know that we can do this by modern calculus, integration by parts, integration by substitution, different kinds of integration methods. But then again, Riemann integral it refers to integration at a time when we didn't have modern integration. So let's talk about Riemann integral here. I mean, to be able to understand Riemann integral, we need to understand some basics. I mean, without those basics, it's impossible for us to delve into this great field of real analysis. So I want to talk about, let's consider a closed, I would say, a closed and bounded interval. Basically, AB, closed and bounded interval AB. Here we go from A to B. It's closed and bounded. What we mean by bounded, that it's not going to go beyond infinity. So it's not like this. This is an open one. It goes to infinity and then infinity like this. All right. So, but then again, we're not talking about infinity. We're going closed and bounded. It can be also bounded on one side and then closed here and open on the other side, or it could be like this. But then again, we're not going to talk about this. All right. So I want to talk about a closed and bounded interval. Now, in a closed and bounded interval, we have our first value, which is A, and the last value is B. So when we have such an interval, we can also have a partition over that interval. Then a partition, let's say P, all right, over this interval can be said to be over this interval. The partition over this interval is a finite and ordered set of points from A to B. A to B including A and B. A to B, including A and B. I want to go over this, but before we go over this, we need to understand the definition of a partition. It is a finite and ordered set. It has to follow a certain pattern, a certain order, and it cannot be mixed up. So let's say I have my interval like this, and this is A, and we have B. Now A is always the first value and B is the last value. So A could be said to be x0, and here I can have x1, x2, x3, dot, 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 and so on until I go to xn minus 1, and here B is going to be equal to xn. You can see now that this interval has been subdivided. We got sub-intervals by those partitions. And so we have the partitions here, all right? And what do we make of this? This interval itself has a certain length, all right? We're going to come to that in just a moment. But before we do that, let's go with a definition. Then P is going to be equal to x0, x1, x2, x3, dot, dot, dot. You go to a general partition, xr minus 1, xr, dot, dot, dot. You go to x, n minus 1, and then xn, where we have x0 being less than x1, less than x2, less than dot, 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 until less than xn, where this is going to be equal to A and this is going to be equal to B. And as can be seen now, therefore it is a finite and ordered set of points from A to B, and we have a finite number of partitions, finite number of points in that set over here. Now, I can have sub-intervals as well, like I said before, but before we go to the idea of sub-intervals, I want to talk about the length of this interval. What is the length of this interval? It's going to be denoted by delta R, and that's going to be B minus A. Now, if I talk about this length here, sorry, wouldn't it be a good idea if I just sort of talk about the partitions first, but then again, I must be taking other examples. Let me talk about partitions, all right? So I want to take another interval, let's say from 0 to 1. Now, we can have over here half as well. Okay, so I can have P is equal to 0, 1. Then I can have P1 is equal to, let's say, 0, half, and 1. As you can see over here, I can have P2, another partition, and this could be subdivided into 1/4 and subdivided into 3/4. So another one is going to be 1/4, 1/2, and then 3/4, and also 1. As you can see now, all these partitions, okay, I can have a third partitions, a number of partitions here, and I can have a third one, which is a 0, and then 1/8. Okay, let me just put a decimal for that matter, 0.2, 0.3, and let's say 0.5, which is basically half. And you can also have 0.75 and 1. So these are partitions. So we can have a family of partitions. So therefore, P of AB could be said to be a family or set of partitions, because we can have many of them, partitions, okay, over the interval AB. So here we are. Now this is what we understand by a set of partitions, family of partitions. Now again, if I talk about these partitions, you can clearly see that this quickly the idea of refinement of refinement of partitions immediately comes into perspective. Why? Because when you look at P1 here, you can see P1 is a subset or equal to P. Also, P2 is a subset or equal to P. P3 is also a subset equal to P. But what about this one? If I say P4 and I say 0, okay, or let's say half, all right. No, sorry, it should have been, sorry, my mistake. It should be P is a subset of P1, subset of P2, subset of P3. Right. And now what we have is P4 over here, 0, half, and let's say we've got let's say 0, half, 3/4. Now, can you see that P, sorry, we've got 0 and 1, and 0, 1 is not here. We've got 0, but 1 is not here. So P is not. Over here, P is not or equal to a subset of P4. So, this is an exceptional case here. Those three ones, so P1, P2, and P3, basically denoted by the star. Okay, so P star, all right, is then a refinement of P. So we talk about refinement, okay? And when I say refinement, I mean refinement of partitions. Refinement of a partition. This is what I mean by this, okay? So the idea for refinement of partitions, it has got to be in this way. that P will be a subset of that refined partition. Otherwise, it's not a refinement of that partition. If it's not a subset, if one of these elements is missing. Okay, now let me just go back to the idea of the length of these partitions. But first of all, I want to draw your attention to the general length itself. Okay, so we have, well, we can also have, let me just come to, we've spoken about refinement of partition. I want to talk now where we have P star, okay, was, I mean, this was a subset. I mean, so if you have P is a subset or equal to P star, then P star, okay, is a refinement of our partition, where P is a subset of P star. Now, I want to talk about the length of a partition, or maybe let's talk about the norm or the mesh of a partition. Now, like I said, we can have different partitions, okay? We can have sub-intervals in partitions. Let's say I have an interval like this, and let's say this is 0, and let's say this is 3/4, and this is 1. You can see, let's say here I've got 6, 7 over 8. You can see that small length here, small length here. This length here is the greatest length. So the normal mesh of the partition, which is now denoted, it is denoted by this symbol here, okay, is the greatest length, okay, is the greatest length of a partition. You see, partition gives rise to the idea of sub-interval. Okay, so like here, we got a sub-interval 0 to, let's say 0 to 3/4 is a sub-interval. Its length can be denoted by its length. Okay, let me just call it delta R for some reason. It's going to be 3/4 minus 0, which is then 3/4. The other one's got this one, the very small length here. The greatest length here is the mesh of the partition. So this is the mesh or the norm of our partition. All right. So now that we've understood refinement of partition, mesh or norm of a partition, I want to go straight into sub-interval. So, like I said, the partition, they give rise to small little sub-intervals, subdivided, so sub-intervals. So we got one here, which is, let me just put it like this, one interval here, another one here, another one here, and then it's going to go on forever. I mean, finitely. So what we have here is sub-interval. I can have the first sub-interval is, let me just call it I1, is going to be equal to x0 to x1. So x0 to x1. Immediately the length of that partition, the length of that sub-interval with partition, sub-interval, okay, it's going to be delta x1. Delta x1 is going to be x1 minus x2. And so delta x1. All right, yeah, because x can be r as well. So I can have delta x2. The second sub-interval will be from x1 to x2. Okay, x1 to x2, the second interval, sub-interval, all right, it's going to be the delta x2 is going to be x2 minus x1. it could have been here x1 minus x0, sorry about that, x1 minus x0, x2 minus x1, x3, I'm going to get x3 minus x2. Dot 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 is going to go up till to, let's say, xn is going to be equal to xn minus xn minus 1. This greater one minus the bigger one. Now, when we look at this, like I said before, you know, the length of length of our interval here, it was b minus a. And so if you add up all the different lengths of these subintervals, now they may not be of equal length, each one of them. Like I said, you know, we can have a greater one and a smaller one. The greatest of all is the norm of the partition, but the smaller ones and the greater ones can be added up. And when you add them up, you should be able to get the length of that whole interval. So over here, the idea of the sum going from, let's say, 1 to n, we have a delta of is equal to delta x1 plus delta x2 plus delta x3 and so on until delta xn. Now if we look at this carefully, the delta x1 was x1 minus x0, so x1 minus x0, then plus x2 minus x1, then plus x3 minus x2 plus, and you're going to go like this, and then you're going to get xn minus xn minus 1. As can we see now, there are cancellation that's going to be taking place. So when we look at this carefully, the x1 is going to cancel with the x1 here. The x0 doesn't cancel out because there's no x0 terms again. So x2 is going to cancel with this one, so xn minus 1 is going to cancel with something else here. x3 is going to cancel with the next one, and I'm left with only two of them, minus x0 and plus xn over here. Now this then becomes xn minus x0. When we look at interval here, x0 was a, so, and then xn was b, so this is b and this is a. And like I said before, you know, it checks out, and it checks out in the sense that, you know, we did say before, if you take the length of each of these intervals and you add them up, you should be able to get the length of the whole interval, the complete entire interval. And this is the idea of adding up the lengths coming up to the whole length of this interval. Right, and yeah, so maybe we could talk about, now that we've spoken about subinterval, refinement of interval, length of interval. In my next video, I might be talking about the infimum and supremum, or maybe I can talk about this right now itself. Okay, so let me just see if there's anything else missing there. I don't think so, and great. So now suppose now you've got an interval AB, and then you've got, let fx be, okay, let fx be a closed and bounded function on AB bounded. So what do we mean by this? Basically now we have, let's say, a function going like this. All right, so, and then somewhere you've got your value of a over here and your value of b over here. So this is a and b. And let's take a general interval. All right, so by saying a general interval, I mean, so let's say x r minus 1. And I got like xr here. Right, so x r over here. Now I want to talk about this interval. Now over this interval here, This is our interval. We have the function going from here all the way to there. So this is our function. This x value of r minus 1 is the lower value here. This one's a bigger value here. So you can see now if your function is fx, so what we're referring to is this is going to give you some value over here. And this value here is called the infimum. So we could talk about the infimum, which is basically denoted by small mr. Small mr is our infimum on fx. Infimum on fx over that interval, such that we got x r minus 1 less or equal to x less or equal to r. And why do we call what infimum is all about? If you look at this interval here, for the infimum, it starts here, goes down here. When you look at the y-axis, this is the greatest value of fx. So the greatest value of fx here, and then if it stops here, that's the greatest value of fx. Then anything below this value here, all these are even less than the greatest length for that particular point over here, particular value. So all the other ones, they are lower bounds, but they are even lower and lower and lower. So the first one is the greatest lowest bound, the greatest lower bound. So this infimum here is what we call a greatest upper bound, because this is going up, right? So it's coming up here. The greatest lower bound. Sorry, greatest. I'm getting confused here. So that's greatest. The greatest lower bound from all the lower bound. From all the lower bounds, it's the greatest lower bound. That's the way I can put it. Jerry. Then I have the supremum. This value here is called the supremum. The supremum of fx. So supremum of fx, you can see for yourself from the board here over this interval that when you look at this value here, it's greater than this infimum. So this is the upper bound here. Upper bound. We have an upper bound over here. So because this is going to go further, the next one is this here. It's going to start here and then up. This now is for this interval. This is the greatest. Okay, the upper bound. That's the lower bound. It's upper bound. So this is lower bound. This is upper bound, roughly speaking. But from that upper bound, it is the lowest upper bound, because any points that come after it on that function is going to give you higher value. So it's going to give you higher value. Therefore, what I'm going to say, this is the lowest upper bound. Lowest upper bound. So we have the greatest upper bound, which is the infimum, and for the supremum, we have the lowest upper bound. Greatest lower bound, lowest upper bound. Because remember, this is an upper bound, like I said before, but any point coming after it is it's going to be even greater and greater and greater. So from the greatest, it is the lowest upper bound. So this is what we call the supremum of our function when it comes to this function over that interval over here, and when it comes basically to infimum and supremum. So in my next video, I'm going to be talking about the lower and upper sum of the Riemann integral, and where this upper bound and lower bound, that is infimum and supremum, will be widely, extensively used for you to be able to actually calculate or find the upper and lower sum of the Riemann integral. So all of that will go into the lower and upper sum, okay, of Riemann integral. So basically we're going to be talking about the Darboux sum. So for now, I hope you've been able to gather as much as possible. Take care and thank you for your attention.